Right now, somewhere in the universe, a star is dying. It is collapsing in on itself with such force that space caves inward, light bends, and time begins to slow. In less than a second, something strange is born, something that will never let go, something that has no surface, no up, no down, only an endless falling inward. This is a black hole. Tonight, we explore the quietest and most powerful objects in the cosmos, places where time stretches thin, where light itself is trapped, and where the rules we thought we understood begin to break apart. They sound terrifying, and yet there is a strange peace in their presence, a gentle reminder that the universe holds wonders beyond our reach. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will drift through the darkness like distant starlight. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever wondered what it would feel like to fall into a black hole, to watch the stars stretch around you as time itself begins to slow? You are not alone. Many listeners fall asleep to these wonders each night. If these facts bring you peace, consider subscribing. It helps others find their way to rest. Take a slow breath now. Feel your body settle into stillness. Let the weight of the day fall away, bit by bit, as we prepare to journey into the deepest reaches of space. There is no rush. The universe has been waiting for billions of years. It can wait a little longer for you. Let us begin. A black hole is not empty. It is a place where space itself falls inward. When we imagine a hole, we picture emptiness, a gap, an absence of something, but a black hole is the opposite of nothing. It is perhaps the most condensed form of something that exists in the entire universe, a region where matter has been compressed so tightly that the very fabric of space and time curves sharply inward, pulling everything with it like water swirling down an invisible drain. Except there is no bottom, no end, only a relentless falling toward a center that defies all description. And if you could somehow peer inside, you would not see darkness in the ordinary sense. You would see space itself bending away from your gaze, folding around ideas that language struggles to hold, a place where even light, the fastest traveler in existence, cannot find its way out. To exist there is to be caught forever. The name black hole did not exist until 1967. For decades, physicists spoke of collapsed stars and gravitational singularities, using long, awkward phrases that never quite captured the strangeness of what they were describing, until the American physicist John Wheeler, during a lecture, casually used the term black hole, and the name stuck immediately, spreading through the scientific community like a spark catching dry leaves, because it was simple and vivid and slightly terrifying, exactly the way language should be when it meets the unknown. And suddenly, this mysterious object had a name that everyone could remember, a name that hinted at danger and wonder and the void all at once, transforming an abstract concept into something the imagination could hold, something that could appear in dreams and conversations and the quiet hours before sleep. Sometimes the right word changes everything. They are invisible, yet they shape everything around them. A black hole emits no light of its own, reflects nothing, and offers no surface for your eyes to rest upon. Yet its presence is felt across vast distances, bending the paths of nearby stars, warping the light of galaxies far behind it, and stirring the dust and gas of interstellar space into glowing spirals that betray its hidden location, like the ripples on a pond revealing where a stone has fallen even after the stone has sunk from view. And astronomers have learned to read these signs, to trace the orbits of stars moving strangely fast around invisible anchors, to measure the heat of matter screaming as it falls inward, to detect the faint gravitational tremors that ripple through space-time when two black holes collide. And in this way, the invisible becomes known through the marks it leaves on everything it touches. Absence speaks louder than presence. Cross the event horizon, and there is no way back. The event horizon is not a wall you would bump against, not a membrane you would feel as you passed through, but an invisible boundary in space where the pull of gravity becomes so overwhelming that even light, traveling at 300,000 kilometers per second, cannot climb back out. And once you cross this threshold, every direction you try to move, forward, backward, sideways, or even upward, leads only deeper inward. Because space itself has curved so severely that all paths point toward the center, like standing at the peak of a hill that has somehow become a pit, where every step, no matter which way you turn, carries you downward, and there is no force in the universe, no engine, no rocket, no miracle of physics that could lift you back across that line. The crossing is gentle, permanent, and silent. At the center lies a point where all known physics breaks down. Beyond the event horizon, the mathematics that describe our universe begin to unravel, and at the very heart of a black hole lies something called a singularity, a point where all the mass has been crushed into an infinitely small space, where density becomes infinite, where the curvature of space and time becomes infinite, where every equation scientists have trusted for centuries returns answers that make no sense, like a compass spinning wildly at the magnetic pole. And this is not simply a gap in our knowledge. It is a signpost marking the edge of human understanding, a place where the rules we use to explain everything from falling apples to orbiting planets simply cease to apply, and physicists suspect that only a new theory, one that unites gravity with the strange behavior of quantum particles, will ever make sense of what happens there. The center remains unknowable for now. Some are smaller than cities, others outweigh billions of suns. Black holes span an almost unimaginable range of sizes, from the stellar variety, born when massive stars collapse, weighing perhaps 10 or 20 times as much as our sun, yet compressed into a sphere only a few kilometers across, small enough to fit within a single large city, to the supermassive giants lurking at the centers of galaxies, containing the mass of millions or even billions of suns, their event horizons stretching wider than our entire solar system. And between these extremes may lie intermediate black holes, elusive objects whose existence astronomers are still working to confirm, and what unites them all is not their size, but their nature, the same fierce gravity, the same inescapable event horizon, the same singularity at the core, scaled up or down like the same melody played on instruments of vastly different pitch. Size is relative, but darkness is absolute. A black hole with the mass of our sun could fit inside a village. If you could somehow compress our entire sun, all 1.9 undecillion kilograms of it, every photon, every atom, every roaring nuclear furnace of hydrogen fusing into helium, into a black hole, the resulting event horizon would be only about 6 kilometers across, a sphere so small that you could walk around its circumference in an afternoon, small enough to nestle into the countryside of a quiet rural village. And yet contained within that modest boundary would be the entire gravitational legacy of a star that has warmed planets for billions of years, now concentrated so tightly that nothing could approach without being drawn inexorably inward, a lesson in how deceptive size can be when gravity is the measure, and how something no larger than a neighborhood could anchor the fate of worlds. Compression redefines everything. And so, from the foundations of what a black hole is, we turn now to how they are born, forged in the death throes of massive stars. Every black hole began as a dying star. A stellar black hole does not appear from nowhere. It is the final chapter in the life of a massive star, a star perhaps 20 or 30 times heavier than our sun, burning through its nuclear fuel over millions of years until there is nothing left to burn. And when that fuel runs out, the outward pressure that once held the star together vanishes in an instant, and gravity, patient and relentless, pulls the core inward with terrible speed, crushing it past the density of ordinary matter. past the density of a neutron star, until it collapses beyond any threshold physics can describe, leaving behind a black hole where a brilliant furnace once blazed, and the outer layers explode outward in a supernova, scattering heavy elements across the cosmos while the core sinks into eternal darkness. Every black hole is a monument to a star that burned too brightly. Only the heaviest stars can collapse into black holes. Not every star ends as a black hole. Only the giants, the rare and massive ones that spend their lives burning through fuel at a furious pace, shine brilliantly for perhaps 10 million years, then die in violent collapse, while smaller stars like our Sun will end their days more gently, swelling into red giants before fading into white dwarfs, dense but stable, cooling quietly over billions of years, never generating enough inward pressure to crush themselves into singularities. And it takes a star at least 20 times heavier than ours, perhaps even heavier, to cross that threshold, to generate enough gravitational force during collapse that nothing can halt the fall. And this means black holes are relatively rare, born only from the heaviest few percent of stars, scattered through galaxies like dark seeds among fields of gentler light. Mass determines destiny, even for stars. The birth of a black hole takes less than a second. After millions of years of slow nuclear burning, a massive star reaches the end of its fuel in a heartbeat of cosmic time. And when the core collapses, everything happens in a fraction of a second, gravity pulling inward with such ferocity that the dense core shrinks from the size of a planet to something smaller than a city in less than a blink, while temperatures soar to billions of degrees and shockwaves rip through the outer layers. And by the time the supernova explosion is visible to distant observers, the black hole has already formed, hidden at the center of the chaos, silent and complete, its event horizon sealed around whatever secrets it now contains. And this stunning brevity is one of the great ironies of the universe, that an object destined to endure for trillions of years is born in an instant. Creation can be startlingly quick. After the explosion, what remains is silence and hunger. When the supernova blast has swept outward, carrying the star's outer layers across light years of space, and seeding the cosmos with the heavy elements that will one day form planets and people, what is left behind at the center is something utterly transformed, a black hole that sits in the suddenly quiet aftermath, pulling gently at the surrounding debris, drawing wisps of gas and dust toward itself like a patient fisherman casting lines into a dark sea. And though the explosion was violent and bright, the black hole itself is silent, offering no light, no heat, no sound, only an endless appetite that will persist for eons, consuming whatever drifts too close, growing ever so slightly with each meal, never satisfied, never full, simply waiting in the darkness for the next particle to fall across its threshold. Hunger that never ends. Once born, a black hole begins to consume everything within reach. From the moment a black hole forms in the aftermath of stellar death, it starts pulling at its surroundings, not aggressively, not explosively, but with the calm, steady inevitability of gravity, drawing in any gas, dust, or unlucky debris that wanders too close, spiraling it inward through a swirling disk that heats to millions of degrees before crossing the event horizon and vanishing from the observable universe forever. And with each meal, the black hole grows slightly larger. Its event horizon expanding ever so gently, its gravitational reach extending a little further, and though the process is slow by human standards, across cosmic timescales, a black hole can consume entire stars, vast clouds of gas, and perhaps even other black holes, growing from a stellar remnant into something truly massive. Appetite is eternal. Some black holes form when two neutron stars collide. Neutron stars are the dense cores left behind when moderately massive stars die, spheres of matter so compressed that a single teaspoon would weigh billions of tons on Earth. And when two of these ghostly remnants orbit each other closely enough, they spiral inward over millions of years, losing energy through gravitational waves, until they finally collide in a cataclysm that outshines entire galaxies for a brief, brilliant moment, scattering heavy elements like gold and platinum across the cosmos. And if the combined mass exceeds a certain threshold, there is nothing that can resist the inward pull, and the merged object collapses into a black hole, born not from a single dying star, but from the violent union of two stellar corpses, a different kind of cosmic birth. Collision creates darkness. From the violence of stellar death, we move to what happens at the boundary, the mysterious event horizon. The event horizon is not a surface, it is a point of no return. If you were falling toward a black hole, you would not feel the event horizon as you crossed it. There would be no barrier, no sudden change in sensation, no sign that anything had happened at all, because the event horizon is not made of anything physical. It is simply the mathematical boundary beyond which escape becomes impossible. The precise distance from the center where the velocity needed to lave exceeds the speed of light, and from the outside, it appears as a dark sphere. A shadow against the glow of surrounding matter, but from the inside, it is indistinguishable from ordinary space, except that every direction now leads inward. Every attempt to flee only accelerates your fall, and you would not know you had crossed until you tried to turn back and discovered that the universe had closed behind you. Boundaries can be invisible. Nothing that crosses the event horizon can ever escape. Once past the event horizon, there is no technology, no engine, no force in the known universe that could possibly carry you back out to safety and freedom, because to escape, you would need to travel faster than light, and nothing with mass can do that, not according to the physics we understand, and even light itself, the fastest thing in existence, bends inward and falls toward the center, unable to climb the steep slope of warped spacetime, which means that anything crossing that threshold matter. Energy, information, is cut off from the outside universe forever, neither seen nor heard nor recoverable, as if it had slipped behind a curtain woven from the fabric of reality itself, a one-way passage leading only deeper into the unknown. The exit does not exist. And as you rest with these thoughts, there is no need to hold onto any of them. Let them pass through you like light falling into the void. Take a breath if you wish, and let your body settle a little deeper. The larger the black hole, the wider its event horizon grows. The event horizon is not fixed at some universal size. It scales directly and proportionally with mass. So a black hole containing 10 times more matter has an event horizon 10 times wider. And this simple relationship means that supermassive black holes, the giants containing millions or billions of solar masses, possess event horizons that stretch across distances comparable to our entire solar system, while smaller stellar black holes, with only a handful of solar masses, have event horizons only a few kilometers across. And curiously, this also means that larger black holes are gentler near their edges, the tidal forces weaker, the stretching less severe, because gravity changes more gradually across a wider horizon, while small black holes can tear you apart before you even get close. Size shapes suffering. A sun-sized black hole would be only 6 kilometers across. If our sun, a sphere of churning plasma nearly 1.5 million kilometers wide, were somehow crushed into a black hole, the resulting event horizon would span just 6 kilometers from edge to edge, a distance you could run in half an hour, small enough to fit comfortably within a modest city, and yet contained within that compact boundary would be all the mass that currently lights our days and warms our world, concentrated so tightly that space itself bends shut around it. And this startling comparison illustrates how extreme the compression of a black hole truly is, not just dense, but impossibly dense, not just heavy, but concentrated beyond ordinary imagination. A lesson in how gravity can fold grandeur into something almost inconceivably small. vastness compressed into a whisper. Stand near the edge, and time itself begins to slow. Einstein's theory of general relativity revealed that gravity is not merely a force tugging on objects, but a curvature in the fabric of spacetime itself. And near a black hole, where that curvature becomes extreme, one of the strangest consequences emerges, the slowing of time, so that if you could hover just outside the event horizon, your wristwatch would tick normally from your own perspective. But to a distant observer watching from safety, your motions would appear sluggish. Your voice stretched into a low rumble, your seconds stretching into their minutes and hours, and the closer you approached, the more severe the effect, until at the very edge, time for you would nearly freeze, while centuries passed for the rest of the universe. A difference so profound that you could outlive stars without ever feeling old yourself. Gravity bends time. Watch someone fall in, and they seem to freeze forever at the edge. If you remained at a safe distance and watched a friend fall toward a black hole, you would see something deeply strange, their descent appearing to slow as they approached the event horizon, their image growing dimmer and redder as light struggled to climb away from the intense gravity, until, at the very edge, they seemed to freeze entirely, their final moment stretched across eternity, never quite crossing, caught forever on the threshold like an insect preserved in amber. And this is not an illusion, but a real effect of time dilation, the light from their final instant taking longer and longer to reach your eyes, redshifting toward invisibility, fading but never vanishing, a ghostly afterimage burned into the fabric of space-time, while they, from their own perspective, crossed the horizon without noticing. Farewells linger endlessly. Fall in yourself, and you would notice nothing at the boundary. From your own perspective, the crossing of the event horizon would be utterly unremarkable to your senses. No flash of light, no sudden jolt, no fanfare announcing your passage into eternal oblivion, because locally, at the exact point where you cross, space-time appears perfectly normal, the curvature gentle enough that you would feel nothing unusual, your heartbeat unchanged, your breathing steady, unaware that you had just become permanently cut off from everyone you ever knew. Unable to send any signal outward, unable to turn back, and only later, as the singularity drew closer and tidal forces began to stretch your body, would you realize that something had gone terribly wrong. But by then, the crossing would be far behind you, already ancient history in your brief remaining future. The door closes silently. Beyond the event horizon lies the singularity, a place where our understanding of the universe reaches its limit. At the singularity, all the mass is crushed into a single point. Beyond the event horizon, as you fall inward, the curvature of space grows ever steeper, the forces ever stronger, until at the very center lies the singularity, a place where theory suggests all the mass of the black hole is compressed into a point of zero volume and infinite density, a concept so extreme that it sounds more like poetry than physics. And yet the mathematics of general relativity leads unavoidably to this conclusion, a place where the numbers become meaningless, where division by zero haunts every equation, and physicists suspect that this is not truly what happens, but rather a sign that our current theories are incomplete, that at such extremes, something else must intervene, perhaps quantum effects, perhaps a new physics altogether, waiting to be discovered. The center is a question, not an answer. The singularity is where the curvature of space becomes infinite. In ordinary circumstances, mass curves the fabric of spacetime gently, planets dimple their surroundings, stars make deeper wells, but at the singularity at the heart of every black hole, the curvature climbs without limit, bending space so sharply that it folds upon itself, where the geometry of the universe, the very stage on which all physics plays out, breaks down entirely, and the equations that normally guide physicists through the cosmos simply stop making sense. Outputting infinities that cannot correspond to real measurements, And this is why the singularity is often described not as a place we understand, but as a wall beyond which our knowledge cannot pass. A reminder that even the most powerful theories have edges, boundaries where their predictions fail, and new ideas must be found. Understanding ends at the infinite. Understanding the singularity may require a new theory of physics. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime, and it has been tested countless times with astonishing precision, yet it breaks down at the singularity, and quantum mechanics, the other pillar of modern physics, governs the behavior of particles at the smallest scales. Yet it does not include gravity in any complete way, and physicists believe that only a theory that unites these two, a theory of quantum gravity, will be able to describe what truly happens at the heart of a black hole, where densities are infinite and sizes are vanishingly small. And though candidates like string theory and loop quantum gravity offer glimpses, none has been confirmed, leaving the singularity shrouded in mystery, a puzzle that calls out for a revolution in understanding. The answer awaits the next Einstein. Some believe singularities may not exist at all. Not all physicists accept that singularities are real physical objects. Some argue that the infinite densities predicted by classical general relativity are simply artifacts of an incomplete theory, that when we finally develop a proper theory of quantum gravity, we will discover that something else happens at the center. Perhaps matter settles into an exotic but finite state. Perhaps spacetime itself is quantized into tiny discrete units that prevent true infinity. Perhaps the structure we call a singularity is replaced by something stranger and more subtle, a core of immense density but not infinite density, hidden behind the event horizon where we cannot directly observe it, waiting for future theories to reveal its true nature, its reality hidden behind the veil of the event horizon. Infinity might be an illusion. Rotating black holes have ring-shaped singularities, not points. Most black holes spin, carrying the angular momentum of the stars that formed them, and a spinning black hole, described by the Kerr solution to Einstein's equations, has a structure different from a non-rotating one, with its singularity stretched not into a point but into a ring, a circle of infinite density lying at the center of a swirling geometry. And the region around it is even stranger, featuring effects like frame dragging, where spacetime itself is pulled along with the rotation. And some theoretical pathways that might, under certain extreme assumptions, allow passage through the ring to elsewhere, though such ideas remain speculative and untested, more mathematical curiosity than practical hope. Yet the rotating black hole reminds us that even within the darkness, complexity abounds. Spin shapes the abyss. Now we turn to one of the strangest effects of black holes, their ability to bend and warp the fabric of space and time. A black hole bends light so severely that even straight lines curve. In the vacuum of space, far from any mass, light travels in perfectly straight paths, the fastest possible trajectory between 2 points, but near a black hole, the fabric of spacetime curves so steeply that those paths bend, light rays skimming close to the event horizon arcing around the black hole, some nearly completing full circles before escaping, others spiraling inward never to emerge. And if you stood near a black hole and looked outward, you might see the entire universe compressed into a ring of brilliant light around the dark center, stars behind the black hole visible beside stars in front of it, images distorted and multiplied by the warped geometry, a visual chaos born from the simplest of principles, that light follows the shape of space, and space follows the pull of gravity. Darkness bends the universe. Gravitational lensing lets us see galaxies stretched and distorted. When light from a distant galaxy passes near a massive object like a black hole or a cluster of galaxies, it bends around the obstacle in a graceful arc. And if we happen to be aligned just right, we can see the background galaxy's image stretched into arcs, sometimes forming complete rings called Einstein rings, or multiplied into several separate images scattered around the lens. And astronomers use this phenomenon, called gravitational lensing, to measure the mass of invisible objects, including black holes, to study galaxies too faint or distant to see directly, and to probe the distribution of dark matter across the cosmos, turning the bending of light into a tool, a cosmic magnifying glass shaped by gravity, revealing secrets hidden in the deep universe. Distortion reveals the unseen. Time passes more slowly near a black hole. One of the strangest predictions of general relativity is that time itself runs at different rates depending on the strength of gravity, and near a black hole, where gravity reaches extremes unknown elsewhere in the universe, this effect becomes dramatic, clocks ticking slower, processes taking longer. And if you could somehow hover close to the event horizon and then return to a distant observer, you would find that far more time had passed for them than for you. Hours for you might be years for them. And this is not a trick of perception, but a real physical phenomenon, confirmed by experiments with atomic clocks on aeroplanes and satellites, extrapolated to the cosmic limit at the edge of a black hole, where time nearly stops for those who linger. Gravity steals time. Spend an hour near the edge, and years may pass on Earth. Imagine descending toward a supermassive black hole, hovering just outside the event horizon where gravity is immense, but survival is still theoretically possible, and spending what feels to you like an ordinary hour gazing out at the stars, and then ascending, returning to a distant space station, only to discover that decades have passed there, that friends have aged and children have grown, and the world you knew has moved on without you. Because for every minute you experienced in the grip of that intense gravity, many times that duration elapsed elsewhere. And while this scenario is beyond our current technology, it is not fantasy, it is the mathematics of relativity carried to an extreme, a consequence of gravity's power over the flow of time. An hour there costs years here. This time dilation is not science fiction, it is real. The slowing of time in strong gravitational fields has been measured directly using precision instruments. Atomic clocks flown on high-altitude aircraft show measurable differences compared to clocks left on the ground, and satellites in the Global Positioning System must account for time dilation to maintain their accuracy, corrections of microseconds per day that, if ignored, would cause navigation errors growing by kilometers, and these gentle effects, tiny near Earth, are amplified enormously near a black hole, reaching extremes where a single day might correspond to centuries elsewhere. And every test we have performed confirms that Einstein was right. That time is not absolute, not universal, but dependent on speed and gravity, bending and stretching in ways our intuition never prepared us for, but that nature demonstrates over and over. The universe follows the rules. Near a black hole, all directions lead toward the center. In everyday life, space gives us freedom, 3 dimensions in which to move up and down, left and right, forward and backward, and we can always turn around and retrace our steps. But near a black hole, especially inside the event horizon, this familiar geometry warps beyond recognition. The curvature of space-time becomes so extreme that every possible direction you could move, every path you could trace through the fabric of reality, ultimately leads inward, toward the singularity. Like being trapped in a river where every current, no matter which way you swim, carries you toward the same waterfall, and even trying to flee only hastens your approach, because time and space have swapped roles inside that boundary, and moving forward in time now means moving deeper into the darkness. Escape becomes geometrically impossible. From the bending of time, we now drift toward another strange phenomenon: what happens to anything that falls in. Fall in, and you would be stretched thin like spaghetti. As you approach a black hole, especially a smaller stellar black hole with its steep gravitational gradient. The difference in gravitational pull between the side of your body closest to the center and the side furthest away becomes enormous tidal forces that would stretch you lengthwise while squeezing you from the sides, elongating your body into a thin strand like pasta being pulled through a die, a process scientists call, with grim and dark humor, spaghettification. And this stretching would happen gradually at first, then faster and faster as you fell deeper, your body extended over hundreds, then thousands of kilometers, atoms pulled apart, consciousness presumably vanishing long before the final moments, a strange and terrible fate that awaits anything approaching the edge of these cosmic abysses. Gravity stretches without mercy. The difference in gravity between head and feet would tear you apart. Imagine falling feet first toward a black hole, and as you descend ever closer still toward that inescapable boundary of no return, your feet, being closer to the source of gravity, are pulled harder than your head, and the difference grows with every passing moment, stretching your spine, pulling your legs away from your torso, exerting forces that no material, not bone, not steel, not any substance known to science, could possibly withstand, and these tidal forces, arising simply from the gradient of gravity over the length of your body, would eventually exceed the strength of the chemical bonds holding you together, tearing you atom by atom into an elongated stream of matter spiraling toward oblivion, a fate written in the geometry of space-time long before you arrived. Tides can be lethal. For smaller black holes, stretching begins before you even enter. Stellar black holes, with event horizons only a few kilometers across, have such steep and punishing gravitational gradients that the tidal forces become deadly while you are still well outside the event horizon, your body beginning to stretch and compress long before you cross that invisible threshold. The spaghettification process claiming your life in open space where no rescue could reach you, visible to distant observers who could watch, utterly helplessly, as you were pulled apart before their very eyes. And this is one reason why stellar black holes are so particularly dangerous, not just the inescapable darkness beyond the horizon, but the lethal approach itself, where survival is absolutely impossible even if you never technically enter the black hole at all, death arriving before the boundary is crossed. Small ones kill early. Supermassive black holes offer a gentler crossing. Paradoxically, the largest black holes are the kindest near their edges, because their event horizons are so enormous, stretching across distances comparable to our solar system, that the gravitational gradient at the threshold is relatively gentle. The difference in pull between head and feet small enough that a falling astronaut could cross the event horizon intact, feeling nothing unusual at that moment, body whole and mind functioning, only to discover afterward that escape was no longer possible, and only later, as they fell deeper and the singularity drew closer, would the tidal forces become fatal. But for a brief window, inside a supermassive black hole, one might actually experience the crossing, contemplate the stars now unreachable, and wonder at the strange fate written in the curvature of space. Giants are deceptively gentle. Once inside, every path leads to the singularity. After crossing the event horizon, there is no direction that leads outward anymore, no possible trajectory that does not end at the singularity regardless of your efforts. And this is not because you lack the speed or the engines to escape, but because the very geometry of space has twisted so severely that all paths, traced forward in time, inevitably bend inward. The singularity lying not so much in a direction as in the future, unavoidable as tomorrow, and whether you accelerate or coast. Turn left or right, try to retrace your steps or push deeper, the result is the same. The singularity grows closer, the tidal forces intensify, and the end approaches with the calm certainty of mathematics working itself out on the grandest possible scale. Destination is fixed. Some theories say falling in might lead somewhere else entirely. Among the more speculative and tantalizing ideas in theoretical physics are proposals that black holes might serve as gateways to realms unknown, that the singularity at their core might not be a dead end, but a passage leading somewhere else entirely, connecting through some unknown geometry to another region of spacetime, perhaps a distant corner of our own universe, perhaps another universe altogether. And while these ideas remain unproven and highly controversial, they are not arbitrary fantasies, emerging instead from mathematical explorations of what might lie beyond the edges of classical general relativity, hints that the apparent finality of the black hole might conceal deeper structures, corridors through the fabric of reality that we do not yet have the tools to explore or even begin to imagine. Perhaps endings are beginnings. And with that curious thought, we now explore the different types of black holes that exist throughout the cosmos. Stellar black holes are born from massive dying stars. The most common type of black hole in the universe is the stellar black hole, formed when a star at least 20 times heavier than our Sun exhausts its nuclear fuel and collapses under its own immense gravity in a catastrophic event, the core crushing inward past the neutron star stage into a singularity wrapped in an event horizon, while the outer layers explode outward in a brilliant supernova visible across galaxies. And these stellar black holes typically weigh between 5 and 30 solar masses, compact enough to fit within a small city, yet heavy enough to warp spacetime dramatically, wandering through the galaxy as invisible remnants of stars that once blazed with the light of millions of suns, now burning nothing, emitting nothing, simply existing in darkness. Death births darkness. Billions of stellar black holes drift silently through our galaxy. Astronomers estimate that the Milky Way alone contains hundreds of millions, perhaps billions, of stellar black holes, the remnants of all the massive stars that have lived and died over the past 13 billion years, scattered throughout the galaxy like seeds from long-vanished flowers, most drifting alone through interstellar space, invisible and undetected, occasionally passing through the gravitational fields of other stars without anyone noticing. And only when a black hole happens to orbit closely with another star pulling gas from its companion and heating it to X-ray brilliance do we catch a glimpse of their presence, which means that for every black hole we know, there are countless others we have never seen, an invisible population of darkness woven throughout the fabric of our cosmic home. The galaxy hides many secrets. Intermediate black holes remain rare and mysterious. Between stellar black holes and the supermassive giants at galactic centers lies a theoretical middle ground, intermediate black holes weighing anywhere from 100 to 100,000 solar masses, objects that should logically exist but have proven remarkably difficult to find, with only a handful of candidates identified over decades of searching across the cosmos, and astronomers remain uncertain how they form, perhaps from the mergers of many smaller black holes. Perhaps from the collapse of unusually massive stars in the early universe, perhaps through runaway collisions in dense star clusters, and their scarcity poses a puzzle. Either they are rarer than expected, or they are hiding in places we have not yet thought to look, or our understanding of black hole formation remains incomplete. Mysteries persist in the middle ground. Let your mind rest for a moment now. The universe is vast, and there is no need to hold all of it at once. Breathe slowly and let these wonders drift through you like distant echoes from deep space. Scientists are still searching for proof they exist at all. The hunt for intermediate black holes has occupied astronomers for many decades, with teams around the world scrutinizing dense star clusters with powerful telescopes, analyzing X-ray emissions from distant galaxies, studying the wobble of orbiting stars, and searching gravitational wave data for signatures that could only come from merging black holes of the right mass range. Yet despite these efforts, definitive proof remains elusive, the candidates few and controversial. And every detection claimed brings debate about whether it truly represents an intermediate black hole or something else entirely. And this ongoing search highlights how much of the universe remains beyond our grasp, how the darkness between stellar and supermassive black holes conceals secrets that may take generations to reveal, assuming they can be revealed at all. Some truths resist discovery. Supermassive black holes contain billions of solar masses. At the extreme end of the black hole spectrum lie the supermassive giants, objects so vast and so incomprehensibly massive that their mass is measured not in tens or hundreds, but in millions, even billions, of solar masses, each one containing more matter than entire star clusters compressed into a region smaller than our solar system. And these cosmic behemoths anchor the centers of galaxies throughout the observable universe. Their gravitational influence, extending across thousands of light years, shaping the orbits of millions of stars, regulating the slow flow of gas that forms new suns, and sometimes, when matter falls toward them in sufficient quantities, blazing with the light of a trillion stars as quasars visible across the observable universe, beacons of destruction that paradoxically reveal the distant past. Scale defies comprehension. Nearly every large galaxy has one at its center. Observations across the past few decades have revealed a surprising and profound truth about the architecture of the cosmos, that nearly every large galaxy, whether a majestic spiral like the Milky Way or an elliptical cloud of ancient stars, harbors a supermassive black hole at its core, a dark anchor around which the entire galactic structure seems to organize itself. And the relationship between galaxy and black hole appears so intimate, with the mass of the central black hole correlating closely with the properties of its host galaxy, that astronomers believe the two must grow together, evolving in tandem over billions of years, feeding each other through processes not yet fully understood, suggesting that black holes are not incidental features, but fundamental components of galactic existence. Galaxies carry darkness at heart. Our galaxy's black hole is called Sagittarius A star. At the center of our own Milky Way, approximately 26,000 light-years from Earth, lies Sagittarius A star, a supermassive black hole weighing roughly 4 million times the mass of our Sun. And although it is currently relatively quiet, producing only modest emissions compared to the blazing quasars in distant galaxies, it still exerts an enormous gravitational influence on the stars surrounding it, with some orbiting at thousands of kilometers per second. Completing their circuits in just a few years, their paths providing the clearest evidence we have for the existence of such massive compact objects. And in the year 2022, the Event Horizon Telescope revealed its silhouette for the first time, a ring of glowing gas surrounding an unlit center, darkness made visible for all of humanity to witness. Our darkness has a name. The largest known black hole weighs 66 billion suns. Among the supermassive black holes discovered thus far, a few stand out as truly monstrous, with the largest confirmed example being TUN 618, a distant quasar located approximately 10 billion light-years away in the depths of the observable universe, whose central black hole weighs an estimated 66 billion solar masses, making it so vast that its event horizon would stretch far beyond the orbit of Neptune if placed in our solar system. A sphere of darkness larger than any structure in our planetary neighborhood, and to contemplate such an object is to confront the extremes that nature permits, the mathematical consequences of general relativity pushed to limits that seem almost absurd, yet are supported by careful analysis of the light from surrounding matter falling eternally inward. Extremes define what is possible. Some black holes may have existed since the very beginning of the universe, born in the chaos of the Big Bang. Primordial black holes may have formed moments after the Big Bang. Unlike stellar black holes, which require the death of massive stars to come into existence, primordial black holes are theorized to have been born in the very first fractions of a second after the Big Bang, when the universe was so incredibly hot, so incredibly dense, and so violently turbulent that slight variations in density could have caused some regions to collapse directly into black holes without ever becoming stars at all. And if they exist, these ancient relics would predate every star. Every galaxy, every structure in the observable universe, carrying within them a snapshot of conditions at the very beginning of time, tiny time capsules of primordial chaos sealed behind event horizons that formed when the cosmos itself was less than a heartbeat old. Origins hide in darkness. Some could be as small as atoms, others as heavy as mountains. The remarkable thing about primordial black holes is that they could span an enormous and truly staggering range of sizes, from objects smaller than an atom yet containing the mass of an asteroid, to giants as heavy as mountains compressed into spaces invisible to the naked eye, and everything in between, because the conditions of the early universe were so varied that density fluctuations of many different scales could have triggered collapse, meaning that if primordial black holes exist, the universe might be filled with invisible objects of wildly different masses, some so small that quantum effects dominate their behavior, others heavy enough to bend starlight as they pass through the galaxy, a hidden population of ancient darkness existing at scales both impossibly tiny and unimaginably compressed. Size means almost nothing here. If they exist, they might explain some of the missing dark matter. One of the great mysteries of cosmology is the nature of dark matter, the invisible substance that outweighs all visible matter in the universe by a factor of 5. And some physicists have proposed that primordial black holes could account for part or all of this missing mass, not exotic particles, but simply black holes formed before the first stars, scattered throughout the cosmos, invisible except through their gravitational effects, pulling on galaxies without emitting light. And while this hypothesis remains controversial, with observations constraining the possible mass range of primordial black holes that could contribute significantly, the idea persists because it would elegantly solve two mysteries at once, explaining both what dark matter is and providing evidence that the early universe was even stranger than we imagined. Darkness might explain darkness. Scientists are hunting for them using gravitational wave detectors. The search for primordial black holes has entered a new and exciting era with the advent of gravitational wave astronomy, because when black holes merge, they send ripples through spacetime itself, and by analyzing the masses of the merging objects detected by LIGO and Virgo and future observatories around the world, scientists can determine whether any fall into ranges that would be difficult to explain through stellar evolution alone, potentially indicating a primordial origin. And some detections have already sparked debate, with certain events involving black holes heavier than expected from stellar processes, raising the tantalizing possibility that we have already heard the collisions of ancient objects formed before the first stars ever ignited, echoes from the dawn of time reaching us as whispers in space-time. Ancient collisions still resonate. Now we turn to one of the most remarkable discoveries about black holes, that they are not entirely black after all. Black holes are not entirely black, they slowly glow. In 1974, the brilliant physicist Stephen Hawking made a startling and revolutionary prediction that overturned the assumption that nothing could ever escape a black hole, proposing instead that black holes must emit a faint glow of radiation. incredibly dim for large black holes, but real nonetheless, arising not from anything escaping through the event horizon, but from quantum effects occurring at its very edge. Where the strange laws of the microscopic world meet the curved geometry of spacetime, and this radiation, now called Hawking radiation, means that black holes are slowly, imperceptibly losing mass, that they are not eternal but finite, doomed over unimaginable timescales to shrink and eventually vanish. A fundamental insight that bridges quantum mechanics and gravity in ways we still do not fully understand. Even darkness fades. Hawking radiation arises from quantum effects at the edge. The mechanism behind Hawking radiation emerges from the peculiar behavior of empty space according to quantum mechanics, which tells us that even the vacuum is never truly empty, but constantly fizzes with pairs of virtual particles popping into existence and annihilating each other almost instantly, borrowing energy from the universe for fleeting moments before paying it back. And near the event horizon of a black hole, something extraordinary happens. Because sometimes one particle of the pair falls into the black hole while its partner escapes into space, and when this occurs, the escaping particle carries away real energy, energy that must come from somewhere, and that somewhere is the black hole itself, which loses a tiny amount of mass with each such escape, a quantum tax levied on the edge of darkness. The edge slowly bleeds. One particle escapes while the other falls in. Imagine the boundary of a black hole as a place where the rules of quantum mechanics and gravity collide in strange ways, where virtual particle pairs born from the vacuum find themselves separated by the event horizon, one partner forever trapped inside while the other flies free. And from the perspective of a distant observer, the escaping particle appears to have been emitted by the black hole itself, carrying positive energy outward while its lost partner, falling inward, effectively carries negative energy that reduces the black hole's total mass. And this delicate quantum dance, happening countless times around every event horizon, produces a faint thermal glow, a radiation so dim that no black hole we know emits enough to be detected, yet so fundamental that it reveals black holes to be dynamic objects slowly surrendering to the quantum realm. Pairs are torn apart. Over vast timescales, black holes slowly shrink and evaporate. Because Hawking radiation carries energy away from a black hole, and because energy and mass are equivalent, every black hole is gradually losing mass, shrinking imperceptibly over time, and the smaller it gets, the hotter it glows, the faster it radiates, in a runaway process that will ultimately consume the entire object, reducing it to nothing. And while this evaporation is unimaginably slow for the black holes we observe today, it is inexorable. A fundamental property of black holes that means none of them will last forever, that even these seemingly permanent monuments to gravity are temporary structures in a universe where entropy always wins, where every object, no matter how powerful, eventually surrenders its existence to the patient flow of time and the ceaseless demands of thermodynamics. Nothing truly endures. A stellar black hole would take longer than the age of the universe to fade. The timescale for Hawking evaporation is almost beyond comprehension, because a stellar black hole of about 10 solar masses would take roughly 10 to the power of 68 years to evaporate, a number so vast that the current age of the universe, at approximately 14 billion years, is nothing but the blink of an eye by comparison, a single grain of sand on a beach stretching to infinity. And this means that every stellar black hole formed since the Big Bang is still essentially unchanged, still holding nearly all the mass it started with, its slow radiation utterly negligible against the cosmic timescales we normally consider, and only in the inconceivably distant future, long after the last stars have died and the universe has grown cold, will these objects finally begin their terminal decline. Patience is measured in eternities. In its final moment, a black hole bursts with energy and vanishes. As a black hole shrinks, its Hawking radiation grows ever hotter and more intense with each passing moment, and in the final stages of evaporation, when only a tiny remnant remains, the process accelerates dramatically, with the black hole glowing brighter and brighter as it loses the last of its mass, until in one final burst of energy, equivalent to millions of nuclear explosions, it vanishes entirely, leaving behind nothing but a flash of gamma rays and high-energy particles that expand outward into space, a brief memorial to an object that once swallowed light itself, and then silence, emptiness, the place where a singularity once existed now indistinguishable from ordinary space, the cosmic wound healed at last, the darkness erased as though it had never been. Death arrives as light. This slow fading raises one of the deepest puzzles in physics, known as the black hole information paradox. When a black hole evaporates, where does the information go? This question strikes at the heart of one of the deepest and most troubling problems in theoretical physics, because according to the laws of quantum mechanics, information cannot be destroyed. The complete description of any system at one moment in time should in principle allow you to reconstruct its state at any other moment, past or future. Yet black holes seem to violate this principle, swallowing matter along with all the information it carries, and then radiating it away as thermal Hawking radiation that appears to contain no information about what fell in. And if this is truly what happens, then black holes represent a fundamental break in the rules governing our universe, a place where the past cannot be recovered from the future, where the cosmos forgets. Memory seems lost. Does information disappear, breaking the laws of physics? Stephen Hawking initially and controversially argued that black holes do indeed destroy information forever and irretrievably, that the thermal radiation they emit truly erases all trace of what fell in forever, a claim that would have profound and troubling implications for physics, suggesting that quantum mechanics must be modified near black holes, that the fundamental reversibility of physical laws fails at the event horizon, and this proposal sparked decades of intense debate among physicists, with many refusing to accept that nature would permit such a violation, arguing instead that the information must somehow survive, hidden in correlations within the Hawking radiation or stored in some other form, and Hawking himself eventually conceded, acknowledging that information likely escapes, though the exact mechanism remains a mystery even now. The laws may yet hold. Some say information is encoded on the event horizon itself. One of the most intriguing and elegant proposed solutions to the information paradox comes from a concept called the holographic principle, which suggests that all the information about what falls into a black hole is somehow encoded on its event horizon, spread across the two-dimensional surface like data written on the skin of a sphere. And this information is then gradually released through subtle correlations in the Hawking radiation, escaping in a scrambled form that theoretically allows the original data to be reconstructed, even if no practical method exists to do so. And if this picture is correct, then the event horizon is not a blank boundary, but a kind of cosmic library, storing everything that enters in a form we do not yet know how to read. The surface remembers. Others believe it leaks out slowly, scrambled beyond recognition. Another view holds that information does eventually escape from black holes over immense timescales, but in a form so thoroughly scrambled, so hopelessly mixed, and encoded across countless particles of Hawking radiation over immense and almost incomprehensibly vast timescales, that reconstructing it would require not only perfect knowledge of every single emitted particle, but also computational resources beyond anything conceivable, making the information effectively lost even while technically preserved. And this perspective suggests that the universe keeps its records, but hides them in a code so complex that no intelligence could ever crack it. The past preserved in principle, but inaccessible in practice. Memories written in a language that no observer will ever learn to read, truth scattered like dust across the expanding cosmos, forever out of reach. Some secrets remain secret. The answer may require a theory we do not yet possess. Ultimately, the black hole information paradox may only be resolved when physicists develop a complete theory of quantum gravity, a framework that successfully unites the principles of quantum mechanics with Einstein's general theory of relativity, the two pillars of modern physics that have never been satisfactorily combined into a unified theory. And until such a theory emerges, perhaps from string theory, loop quantum gravity, or some approach not yet imagined, the fate of information in black holes will remain unclear, a signpost pointing toward the limits of our current understanding, a reminder that the deepest questions about the universe may require concepts and mathematics that humanity has not yet discovered, truths waiting beyond the horizon of present knowledge, perhaps forever out of reach to current methods. Understanding awaits future minds. From these theoretical mysteries, we now look at how scientists have actually observed these invisible objects. The first black hole detected was Cygnus X1 in 1971. For decades, black holes existed only as mathematical curiosities, predictions of Einstein's equations that many physicists doubted would ever be found in nature, until astronomers turned their attention to a powerful X-ray source in the constellation Cygnus, designated Cygnus X1, and discovered that this brilliant beacon of high-energy radiation was being produced by matter falling toward an invisible object far too massive to be a neutron star by any known model. And the conclusion was inescapable: this had to be a black hole, a stellar corpse pulling gas from its companion star and heating it to millions of degrees as it spiraled inward. And with this discovery, black holes crossed from theory into reality, from elegant mathematics into the catalog of objects that actually populate our universe. The invisible became undeniable. It pulls matter from a companion star, heating it until it glows. Cygnus X1 belongs to a binary system, where a blue supergiant star orbits close enough to the black hole that its outer atmosphere is being steadily stripped away, drawn by gravity toward the invisible companion. And as this stolen gas accelerates and falls inward, it heats to extraordinary temperatures, millions of degrees, releasing torrents of X-ray radiation that space telescopes can detect across thousands of light years. And this process has been going on for thousands of years. The star slowly sacrificing itself to feed its dark partner, a cosmic dance where one grows weaker while the other remains forever hungry. And the brilliant X-ray glow is both a signal and a warning, telling us that here, in this distant corner of the galaxy, matter is meeting its end. Theft produces brilliance. We find black holes by watching how stars orbit invisible objects. Black holes emit no light of their own whatsoever, and even their event horizons are impossibly small by astronomical standards when compared to the distances between stars. Yet we can find them by carefully observing their gravitational influence on nearby stars, watching as suns swing around invisible partners at speeds that can only be explained by the presence of enormous mass concentrated in a tiny space, and by tracking these stellar orbits over years or decades. Measuring the wobbles and accelerations with exquisite precision, astronomers can calculate the mass and location of the unseen companion, confirming its nature as a black hole when no other explanation fits the data, turning absence into evidence, using the behavior of light to reveal the presence of something that has no light to give. Shadows cast gravitational fingerprints. Falling matter forms a glowing accretion disk. When gas and dust fall toward a black hole from the surrounding environment, they rarely plunge straight in without resistance, because angular momentum causes the material to spiral inward, forming a flattened disk that orbits the black hole like water swirling around a drain. And within this accretion disk, friction between layers moving at different speeds generates enormous heat, raising the temperature to millions of degrees near the inner edge, producing radiation across the electromagnetic spectrum. From infrared to X-rays, and these accretion disks can outshine entire galaxies, making them visible across billions of light years, bright enough to illuminate the distant corners of the cosmos. And it is the disk, not the black hole itself, that we observe, a glowing halo around a sphere of invisible absence. Light surrounds darkness. In 2019, we captured the first image of a black hole. For generations, black holes existed only as mathematical models and artistic interpretations, visualizations created by scientists and artists trying to imagine what these invisible objects might look like if we could somehow see them, until April 2019, when the Event Horizon Telescope collaboration released an image that changed everything: a blurry orange ring of glowing gas surrounding a dark central shadow. The silhouette of a supermassive black hole seen for the first time by human eyes, and this achievement required linking radio telescopes across the entire Earth, effectively creating a detector the size of our planet, all to capture a glimpse of an object small enough to fit within our solar system, yet located so far away that its light had been traveling for 55 million years. The impossible was photographed. Pause here for a breath. Let the image of that distant shadow settle softly in your mind. You do not need to understand everything. Simply let the wonder of it carry you toward rest. That shadow belonged to a black hole 55 million light-years away. The black hole captured in that first historic image lies at the center of Messier 87, a giant elliptical galaxy in the constellation Virgo some 55 million light-years away, and contains an estimated 6.5 billion solar masses, making it one of the most massive black holes ever discovered. And because the light we received had been traveling for 55 million years, we were seeing the black hole not as it exists today, but as it was when dinosaurs still walked the Earth. And this extraordinary distance made the technical challenge even greater, requiring unprecedented coordination and computational power to transform radio signals into an image. Yet the result revealed a shadow precisely matching theoretical predictions, confirmation that Einstein's century-old equations describe reality with astonishing accuracy. Time travel through light. In 2022, we saw our own galaxy's black hole. 3 years after imaging the distant giant in Messier 87, the Event Horizon Telescope team released an even more personal portrait, an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, a smaller and more chaotic subject that proved surprisingly difficult to photograph because gas swirls around it so quickly that the appearance changes within minutes, unlike the steady glow of larger black holes where material orbits more slowly. And yet the team succeeded, revealing another glowing ring around a dark center, proof that the monster at the heart of our galaxy looks much like its cousins elsewhere, a window onto the gravitational anchor around which 400 billion stars, including our own sun, slowly orbit. Home has darkness at its heart. Gravitational waves let us hear black holes collide. In September 2015, the Laser Interferometer Gravitational Wave Observatory, known simply as LIGO, detected something unprecedented that would change astronomy forever. Ripples in the fabric of spacetime itself, arriving at Earth from deep space after traveling for over 1 billion years. And these gravitational waves, predicted by Einstein a century earlier, but never before observed directly, carried a clear signature. The final moments of two black holes spiraling together and merging into one, releasing more energy in a fraction of a second than all the stars in the observable universe combined. And this detection opened an entirely new way of observing the cosmos, no longer limited to light, but now able to sense the vibrations of spacetime itself, hearing the universe as well as seeing it. Spacetime learned to sing. The first waves came from a collision over 1 billion light-years away. That historic first detection, designated GW 150914, originated from the merger of two stellar black holes, one weighing 36 times the mass of our Sun and the other 29, spiraling together in their final moments until they collided and combined into a single black hole of 62 solar masses, with the missing 3 solar masses converted entirely into gravitational wave energy radiating outward in all directions. And this event, happening over 1 billion years before dinosaurs existed on Earth, sent ripples across the cosmos that were so faint by the time they reached us that they displaced LIGO's detectors by less than 1,000th the width of a proton. Yet the signal was unmistakable, a chirp rising in frequency as the black holes accelerated toward their final union. Distance compressed into whispers. Dozens of black hole mergers have now been observed. Since that first historic and groundbreaking detection, LIGO and its international partners have recorded dozens of black hole mergers from across the cosmos, each event adding to our understanding of how these objects form, how they find each other across the vastness of space, and how they behave in their final catastrophic moments. And the growing catalog has revealed surprises: black holes heavier than expected from stellar evolution, pairs with unusual spin orientations, mergers happening more frequently than some models predicted. And with each observing run, as the detectors grow more sensitive, more events appear, painting an increasingly detailed picture of a violent universe where black holes routinely collide, reshaping themselves in bursts of gravitational energy that echo through space-time like thunder from distant storms. The catalog grows ever richer. Now we turn our attention to the supermassive black holes that anchor galaxies, silent guardians at the center of cosmic spirals. Supermassive black holes contain the mass of billions of suns. We have already touched upon the enormity of supermassive black holes, but the concept bears repeating because it is so profoundly difficult to truly grasp with human intuition. These objects contain the mass of millions to billions of suns compressed into a region that, while enormous by human standards, is minuscule compared to the galaxies they inhabit, and the largest of them weigh as much as 40 billion solar masses or more. Concentrations of matter so extreme that they warp spacetime around them for millions of light years in every direction, influencing the orbits of billions of stars that know nothing of the darkness at their galaxy's center, only that some unseen force guides their paths through the cosmic void, an invisible hand shaping the motions of galaxies. Compression defies imagination. Their event horizons can be larger than our entire solar system. The event horizon of a supermassive black hole is proportional to its mass, meaning the largest of these objects have boundaries that stretch across distances comparable to our solar system. Spheres of no return that would swallow not just the Sun, but all the planets, the asteroid belt, and the Kuiper belt with room to spare. And if you were falling towards such a giant, you might not even notice the event horizon when you crossed it. The transitions so gentle at these scales that nothing dramatic would mark your passage from the outside universe to the interior from which escape is impossible. Only later would you realize, as the singularity drew nearer and tidal forces began to rise, that you had already passed the point of no return. Patience before destruction. How they grew so large so quickly remains a mystery. One of the deepest puzzles in modern astrophysics is how supermassive black holes came to be in the first place. because standard models of stellar evolution and black hole growth suggest that building something with billions of solar masses should take longer than the current age of the universe. Yet we observe brilliant quasars powered by such giants less than 1 billion years after the Big Bang, implying that these objects grew to enormous sizes in a remarkably short time. And no satisfactory explanation has emerged to account for this rapid and seemingly impossible growth. Whether through unusually effective accretion, many mergers of smaller black holes, or formation mechanisms entirely unlike anything we understand today, leaving cosmologists puzzled and searching for answers in the early universe. Speed defies explanation. Some say they formed from collapsing gas clouds, not stars. One proposed solution to the puzzle of rapid supermassive black hole growth is the direct collapse scenario, which suggests that in the early universe, massive clouds of primordial gas might have collapsed directly into black holes, weighing tens of thousands of solar masses without ever forming stars first, bypassing the slow process of stellar evolution entirely. And if such events occurred in the chaotic conditions of the early cosmos, they would have produced seed black holes large enough to grow into supermassive giants through relatively modest accretion over the available cosmic time. And while direct evidence for this pathway remains elusive, the theory offers an elegant solution to the problem of how the earliest quasars could have existed so soon after the cosmos began, answering one puzzle while raising many others. Shortcuts may exist. Others propose they grew by merging and devouring matter. An alternative pathway to supermassive black hole formation involves the gradual and patient accumulation of mass through a combination of accretion and mergers, with smaller black holes consuming gas, dust, and stars over billions of years, while occasionally combining with other black holes when their host galaxies collide in the cosmic dance of gravity. And over cosmic time, these processes could build black holes of tremendous size. Though calculations suggest this method alone may not be fast enough to explain the earliest supermassive black holes, leading many astronomers to suspect that some combination of mechanisms, perhaps including direct collapse seeds followed by aggressive growth, is required to explain the full diversity of supermassive black holes observed across cosmic history, a puzzle with many pieces still missing from our understanding. Growth takes many forms. From their mysterious origins, we now explore the relationship between supermassive black holes and the galaxies that surround them. A galaxy's black hole and its stars seem to grow together. One of the most remarkable discoveries about supermassive black holes is their intimate and truly profound relationship with their host galaxies, revealed through a tight correlation between the mass of the central black hole and various properties of the galaxy surrounding it, particularly the velocity dispersion of stars in the galactic bulge. And this relationship implies that black hole and galaxy evolution are deeply linked in ways we barely understand. That feedback from the active nucleus somehow regulates star formation, or that both grow from the same underlying processes, and this coevolution suggests that supermassive black holes are not incidental inhabitants, but fundamental architects of galactic structure, shaping their hosts even as they are shaped by them, locked in a cosmic embrace that spans billions of years. Partners in cosmic development. Larger galaxies have larger central black holes. The correlation between galaxy size and black hole mass extends across an enormous and remarkable range of scales that spans many orders of magnitude, from dwarf galaxies with modest central black holes of a few 100,000 solar masses to giant ellipticals harboring monsters weighing tens of billions of suns. And this scaling relationship holds with surprising consistency, suggesting that whatever processes link black hole growth to galactic evolution operates similarly across vastly different environments and cosmic epochs, a universal connection that transcends the particular details of any individual system, as though nature follows a recipe that ensures the central darkness always matches the brightness surrounding it, a cosmic balance written into the very structure of existence, a harmony that emerged from the violence of cosmic evolution. Proportion governs all. When a supermassive black hole feeds, it becomes a quasar. When vast quantities of gas fall toward a supermassive black hole at tremendous speeds and with devastating force, the accretion disk surrounding it can blaze with unimaginable brilliance, producing what astronomers call a quasar or quasi-stellar object, named because these phenomena appear star-like in telescopes despite being located billions of light-years away. Their luminosity, powered not by nuclear fusion like ordinary stars, but by the conversion of gravitational energy as matter spirals violently toward the event horizon, releasing more energy than 100 galaxies combined from a region smaller than our solar system. And these quasars represent black holes in their most dramatic phase, actively devouring their surroundings and announcing their presence across the observable universe, beacons of cosmic consumption. Bright testaments to the power of gravity, hunger creates splendor. Quasars can outshine entire galaxies. The luminosity of a powerful quasar is almost impossible to truly comprehend in any meaningful human terms, with the brightest examples releasing more energy every second than 1 trillion suns, enough to outshine all the hundreds of billions of stars in their host galaxy, combined by factors of 10 or 100 or more. And these cosmic beacons are visible across vast expanses of space and time, allowing astronomers to study the early universe by observing quasars that formed when the cosmos was less than 1 billion years old, their light carrying information about the conditions that existed long before our sun and planet came to be, messengers from the distant past still arriving at our telescopes today, light that began its journey before Earth existed. Brilliance travels eternities. Jets of energy from black holes stretch for thousands of light years. Some supermassive black holes produce relativistic jets, narrow beams of plasma and energy that shoot outward from the poles of the accretion disk at speeds approaching the speed of light, extending for thousands or even millions of light years into the vast emptiness of intergalactic space. And these jets carry enormous amounts of energy away from the black hole, heating the surrounding gas, carving bubbles in the intergalactic medium, and influencing the evolution of galaxies far beyond the one containing the black hole itself. And the precise mechanism that produces these jets remains mysterious, involving complex interactions between the rotating black hole, the magnetic fields threading the accretion disk, and the hot plasma falling inward, a dance of forces we do not yet fully understand. Energy escapes in narrow streams. These jets can shape how nearby stars are born. The energy carried by relativistic jets does not simply dissipate into empty space, but interacts dramatically and powerfully with the surrounding environment on scales that beggar the imagination, heating interstellar and intergalactic gas, preventing it from cooling and collapsing into new stars, and in some cases shutting down star formation across entire galaxies for millions of years. While in other circumstances, the jets can compress gas clouds and trigger the birth of new stars along their turbulent edges. And this feedback mechanism means that supermassive black holes, despite being located at the centers of galaxies, can influence star formation processes thousands of light years away, acting as cosmic regulators that determine when and where new suns will eventually ignite, their presence felt far beyond the gravitational reach of their event horizons. Darkness governs birth. From the influence of black holes on galaxies, We now consider what happens when galaxies collide and their black holes meet. When galaxies collide, their black holes slowly spiral inward. Gravitational interactions between galaxies are remarkably common across cosmic history, and when two large galaxies merge over countless eons in a slow collision, their central supermassive black holes begin a slow dance that can last billions of years. As the merging galaxies stir together and the black holes lose angular momentum through countless interactions with the surrounding stars and gas, spiraling ever closer toward the common center of mass. And this process sees the black holes transition from widely separated objects orbiting within a combined galaxy to a tightly bound binary system where their mutual gravitational influence dominates completely, a pairing that sets the stage for one of the most violent events in the universe, a merger written in gravity, foretold by the laws of physics. Collision is inevitable. Eventually, the two black holes merge in a violent flash. When a binary supermassive black hole has spiraled close enough that gravitational wave emission becomes truly significant and dominates the orbital dynamics, the final merger happens remarkably quickly in cosmic terms, with the two event horizons rushing together and combining into a single, larger black hole in a burst of gravitational radiation that carries away a significant fraction of the total mass as pure energy rippling through space-time. And this merger represents one of the most energetic events in the cosmos, releasing more power in a fraction of a second than all the stars in the observable universe combined, yet producing no light whatsoever, only waves in the fabric of space itself, invisible to ordinary telescopes, but thunderous to instruments designed to hear the whispers of gravity. Union explodes silently. The merged black hole can be kicked out of its galaxy entirely. When two black holes merge, the gravitational waves they emit do not radiate equally in all directions, and this asymmetric emission carries momentum, which means the merged black hole receives a recoil kick that can send it hurtling away from its original location at speeds of thousands of kilometers per second, fast enough in extreme cases to escape the gravitational pull of the host galaxy entirely and forever, launching the newly formed and enlarged supermassive black hole on a trajectory that will carry it into the darkness of intergalactic space, a wandering cosmic nomad ejected from the system that created it, leaving behind a galaxy without a central anchor for the first time in billions of years, a cosmic orphan set adrift among the stars. Merger can mean exile. Our Milky Way will collide with Andromeda in 4 billion years. The Andromeda Galaxy, visible to the naked eye as a faint smudge in the night sky on clear evenings far from city lights, is approaching the Milky Way at roughly 110 kilometers per second, and in approximately 4 billion years, the two galaxies will begin their first passage through each other, their hundreds of billions of stars swirling together in a gravitational dance that will ultimately produce a single, larger galaxy. And while individual stellar collisions will be extremely rare due to the vast distances between stars, the overall structure of both galaxies will be dramatically transformed, spiral arms disrupted, star formation triggered and then suppressed, and the shapes we know today erased forever in the cosmic remodeling to come, a transformation on the grandest possible scale. Distant collision approaches. When it does, the two central black holes will eventually meet. As the Milky Way and Andromeda merge over the following billions of years in a slow cosmic dance, their central supermassive black holes, Sagittarius A star and its Andromeda counterpart weighing perhaps 100 million solar masses, will gradually spiral toward the center of the combined galaxy, their orbits decaying through dynamical friction as they interact with the surrounding stars and gas, until eventually they form a tight binary system, and then, releasing a final burst of gravitational waves that ripples through space-time, merge into a single supermassive black hole at the heart of the new galaxy, a union that will mark the final chapter of both ancestral systems, though no humans will remain to witness it unless our descendants have spread far beyond this corner of the cosmos. Futures converge in darkness. Now we drift towards some of the more speculative ideas surrounding black holes, places where science meets imagination. Some say black holes might be gateways to other universes. Among the more speculative ideas in theoretical physics is the astonishing proposal that black holes might not simply destroy what falls into them, but instead connect to other vastly distant regions of space-time, perhaps other universes entirely, with matter entering through the event horizon emerging somewhere else in a process we cannot observe or verify with any current technology. And while these ideas arise from legitimate extensions of general relativity and quantum mechanics, they remain firmly in the realm of theory, untested and perhaps forever untestable, occupying that fascinating boundary where scientific reasoning meets the limits of empirical verification, where imagination and mathematics together explore possibilities that nature may or may not have chosen to realize, dreams shaped by equations, visions born of logic and wonder. Speculation dreams grandly. Wormholes could connect distant points through a tunnel in space-time. A wormhole, also known as an Einstein-Rosen bridge, after the physicists who first described the concept in the 20th century, is a theoretical structure in space-time that would create a shortcut between vastly distant locations, allowing travel across immense distances without traversing the intervening space. A cosmic tunnel that could link galaxies or perhaps even different universes altogether. And while the mathematics of general relativity permits such structures, no observational evidence suggests they exist, and the conditions required to create and stabilize them may be impossible to achieve, requiring exotic forms of matter with negative energy densities that have never been observed and may not exist in nature, leaving the dream a mathematical curiosity for now, a path that equations permit but nature may forever deny. Tunnels remain theoretical. The mathematics allows for wormholes, but none have been found. Despite decades of searching and persistent theoretical development across multiple scientific disciplines, astronomers have found absolutely no evidence for naturally occurring wormholes in the observable universe. No gravitational signatures that would indicate the presence of these exotic structures. No phenomena that cannot be explained by conventional physics. And while this absence does not prove that wormholes are impossible, it suggests that if they exist at all, they are either extremely rare, inherently unstable, or located in regions of space-time we cannot possibly access with any foreseeable technology, and the dream of using wormholes for interstellar travel or communication remains, for now, firmly in the realm of science fiction despite its mathematical foundations. A hope without evidence, but not without possibility. A dream that persists despite the silence of observation. Searches yield emptiness. Even if they exist, they would likely collapse instantly. Most theoretical analyses suggest that any wormhole formed naturally in the depths of spacetime would be catastrophically unstable. Collapsing faster than light could travel through it, pinching shut before anything could possibly pass from one end to the other. And while some physicists have proposed that exotic matter with negative energy density might stabilize a wormhole and hold it open, such matter has never been observed and may violate fundamental principles of quantum mechanics, leaving the possibility of stable, traversable wormholes as an open question that physics cannot yet definitively answer. A tantalizing maybe suspended between the permissible and the impossible, a question mark written in the equations of physics, a puzzle that may never be solved with current understanding, a boundary where physics admits its own limitations. Stability may be forbidden. Let your thoughts grow still now. The edge of knowledge is a quiet place where certainty fades and wonder begins. Take another slow breath. Let your body soften into the night. Our entire universe might exist inside a larger black hole. One of the most mind-bending and philosophically troubling proposals in cosmology suggests that our entire observable universe, with its hundreds of billions of galaxies and all the space between them, might exist inside a black hole that formed within a larger parent universe, and that what we call the Big Bang was actually the formation of this black hole from the perspective of that outer reality. And while this idea remains highly speculative and controversial even among theorists, it offers an intriguing perspective on the nature of cosmic origins, suggesting that creation and destruction might be two perspectives on the same event, that every ending somewhere contains a beginning somewhere else, that the darkness we observe at the centers of galaxies might contain infinities of light. Perhaps we are interior. Every black hole might contain a new universe within it. Extending this idea further into its strangest and most mind-bending implications that challenge our understanding, some theorists have proposed that every black hole in our universe might itself contain a new universe, a cosmos that forms whenever a singularity is created, connected to ours through the event horizon, perhaps following different physical laws, perhaps identical to our own. And if this picture is correct, then the universe is not a single bubble, but an infinite hierarchy of nested realities, black holes giving birth to baby universes that contain their own black holes that birth their own universes, a fractal structure of creation extending beyond comprehension, though whether any of this is true remains unknown and perhaps permanently unknowable from within our own cosmic bubble, a mystery beyond observation. Universes may nest forever. The holographic principle says all information is stored on the surface. The holographic principle, arising from theoretical physics and the careful study of black holes over many decades of research, proposes that all the information contained within a region of space can be fully described by data encoded on the boundary surrounding that region, suggesting that the three-dimensional world we experience might be a kind of projection from a two-dimensional surface, much like a hologram projecting depth from a flat image. And this remarkable idea emerged from attempts to understand the entropy of black holes, finding that the information content scales with surface area rather than volume, a discovery with profound and unsettling implications for the nature of space, time, and reality, suggesting that the universe may be fundamentally different from how it appears to our senses. Surfaces hold depths. Our three-dimensional world might be a projection of a flat boundary. If the holographic principle is correct and represents the true nature of reality, then the familiar three-dimensional space in which we move and breathe and think might not be fundamental at all, but rather an emergent phenomenon projected from a lower dimensional reality, with all the information that defines our existence encoded on some cosmic boundary that we cannot see or detect directly. And while this sounds like science fiction, it arises from rigorous mathematical analysis and is taken seriously by many theoretical physicists working on the unification of quantum mechanics and gravity, representing one of the most radical possible revisions to our understanding of what physical reality actually is, a reconceptualization that would reshape everything we believe about existence, turning our understanding of the universe inside out. Depth might be illusion. Black holes may play a role in the universe's final fate. In the far, far future, long after the last stars have burned out and the cosmos has grown utterly cold and eternally dark beyond all recognition, black holes will be among the last remaining objects in the entire universe, slowly evaporating through Hawking radiation over timescales so vast that the current age of the universe seems like an instant. And eventually, even these eternal-seeming structures will fade completely, their final explosions marking the last energetic events in a dying cosmos. Until only the faint background radiation and scattered particles remain, drifting forever through empty space. And in this sense, black holes represent both the endpoints of stellar evolution and the final chapter of cosmic history, the last lights to go out before the infinite darkness that may follow. Endings stretch forever. And now we approach the final wonders, contemplating black holes through history, culture, and the future of exploration. Long ago, scientists predicted gravity so strong that light could not escape. The concept of an object so massive and compact that not even light could escape its gravitational pull predates modern physics by over 2 centuries, emerging first as a thought experiment based on Newtonian gravity that was considered by several natural philosophers, which showed that any body with sufficient mass concentrated in a small enough space would have an escape velocity exceeding the speed of light, trapping radiation and rendering the object invisible to distant observers. And while the physics underlying these early predictions was incomplete, the fundamental insight proved correct, anticipating by centuries the black holes that general relativity would later describe with mathematical precision, a glimpse of truth before the tools existed to prove it, a flash of insight that would wait centuries for confirmation. Ancient intuition preceded proof. In 1783, John Michell imagined dark stars. The English natural philosopher John Michell, carefully considering the implications of Newtonian gravity for light in the late 18th century, which he assumed to be composed of particles influenced by gravitational attraction, calculated that a star with the same density as the Sun, but roughly 500 times larger, would have a surface gravity so strong that light could not escape. And he proposed that such invisible bodies might exist throughout the universe in great numbers, detectable only through their gravitational influence on nearby visible stars, a remarkable prediction that anticipated core features of what we now call black holes, made over a century before Einstein transformed our understanding of gravity and light, a vision far ahead of its time, a dream waiting for the mathematics to catch up. Imagination outpaced instruments. Pierre-Simon Laplace had the same idea independently. A few years after Michell's groundbreaking work in England, the French mathematician and astronomer Pierre-Simon Laplace independently arrived at the same conclusion, publishing his speculations about invisible stars in his monumental treatise on celestial mechanics. And while Laplace later removed this discussion from subsequent editions, perhaps recognizing the limitations of the Newtonian framework for addressing such questions, his work demonstrated that the idea of gravitationally collapsed objects was not merely an idle fancy, but a natural consequence of the physics known at the time, waiting only for a more complete theory to give it proper form, a seed planted in the soil of classical physics, waiting patiently to bloom, an idea whose time had not yet come, waiting for a century to find its proper expression. Great minds converge. Karl Schwarzschild solved the mathematics in 1916. Just months after Einstein published his revolutionary general theory of relativity in 1915, a theory that would transform our understanding of the cosmos, the German physicist Karl Schwarzschild, serving on the Russian front during the First World War, found the first exact solution to Einstein's field equations, describing the curved spacetime around a spherically symmetric mass. And this solution revealed the existence of a critical radius, now called the Schwarzschild radius, at which the effects of gravity become so extreme that an event horizon forms, though Schwarzschild himself died shortly afterward and did not live to see his mathematics interpreted as describing real objects in the universe, his equations waiting decades to be fully understood, his legacy written in the geometry of space-time, a gift to future generations. War could not stop mathematics. For decades, black holes were seen as mere mathematical oddities. Even after Schwarzschild's elegant solution demonstrated that general relativity permitted such extreme and troubling objects to exist within our universe, many physicists, including Einstein himself, doubted that nature would actually produce them, viewing the singularity at the center of a black hole as a mathematical pathology rather than a physical reality. And it was not until the 1960s that theoretical work by Roger Penrose, Stephen Hawking, and others established that gravitational collapse to a singularity was inevitable under certain conditions, and observational evidence from X-ray astronomy began revealing sources that could only be explained by matter falling violently into compact objects far denser than ordinary stars, objects that theory had predicted, but minds had stubbornly and long resisted, a truth too strange for immediate acceptance. Theory struggled to accept itself. Today we know they are real and scattered throughout every galaxy. The debate is now settled, the evidence overwhelming and beyond any serious dispute, and astronomers now understand that black holes are not rare curiosities, but essential and fundamental components of the cosmic landscape. With stellar black holes numbering in the hundreds of millions within our galaxy alone, and supermassive black holes anchoring the centers of virtually every large galaxy observed, their existence confirmed through gravitational wave detections. Direct imaging by the Event Horizon Telescope and decades of observations tracking the orbits of stars around invisible masses, transforming black holes from theoretical speculation into established astronomical fact, objects as real as planets and stars, simply stranger, simply more wondrous than anything we once dared to imagine, confirmed beyond any reasonable doubt, their presence written across the cosmos. Reality exceeded imagination. Future telescopes will reveal even more of their secrets. The next generation of telescopes and advanced observatories, both on the ground and in space, will push our ability to study black holes to new and unprecedented extremes that we can barely imagine today, with more sensitive gravitational wave detectors capturing mergers at previously undetectable distances, space-based interferometers listening for the low-frequency rumble of supermassive black hole binaries, and imaging arrays with even better resolution revealing the detailed structure of accretion disks and jets around nearby black holes. And each technological improvement will bring new surprises, new puzzles, and new opportunities to rigorously test our theories against the reality of these extraordinary objects, continuing a journey of discovery that is still only beginning, reaching ever deeper into the darkness, revealing wonders we have not yet imagined. Instruments sharpen with time. Perhaps one day, the deepest questions about black holes will be answered. What happens at the singularity, how information escapes, whether wormholes truly exist, what lies beyond the event horizon, these fundamental questions remain open and continue to fascinate scientists around the world, challenging physicists to develop new theories that unify quantum mechanics and gravity, revealing the nature of space-time at its most fundamental level. And while we cannot know whether these questions will ever be fully answered, the history of physics suggests that progress often comes in unexpected leaps, that mysteries which seemed permanent have yielded to insight and experiment, and that the black holes which now guard so many secrets might one day become as well understood as the stars that gave them birth, their darkness finally illuminated by human understanding, the unknown slowly yielding to patient inquiry. Understanding may yet arrive. And so our journey through the silent realm of black holes draws softly to a close. We have wandered through the collapse of dying stars and the birth of darkness, past the edge where light gives up its struggle and time bends toward infinity. We have glimpsed the singularities that defy understanding, the event horizons that mark the boundary of the known. From the smallest stellar remnants to the supermassive giants that anchor galaxies, from the faint glow of Hawking radiation to the thunderous ripples of colliding black holes, we have traced the shape of the invisible. And through it all, the universe has remained patient, holding its mysteries close, waiting for those who dare to listen. If these wonders have brought you peace, consider subscribing to join this quiet community. There are more journeys ahead, more facts to drift through, more nights to spend among the stars. And if you found tonight restful, a like or a comment helps others find their way here too. Right now, as you lie in stillness, the supermassive black hole at the center of our galaxy is slowly turning, 4 million times heavier than the sun, yet silent, patient, unreachable. Light from distant stars is bending around it, and time is subtly slowing near its edge. You are part of a galaxy that carries this ancient shadow at its heart, and tonight, as you rest, that connection remains. Let your eyes grow heavy now if they wish. Let your breathing slow, deep and unhurried, like the drift of starlight across the void. Feel your shoulders soften, your jaw release, your hands rest open and still. There is nothing left to hold, nothing left to think about. Let the weight of the day fall away and let your body settle into the night. Tonight, as you sleep, black holes continue their silent work. Stars collapse in distant corners of the cosmos. Event horizons shimmer at the edge of forever. Gravitational waves ripple outward from collisions you will never see. Supermassive giants anchor galaxies, and somewhere, light is falling toward darkness, never to return. You are a small, warm presence within this vast cosmic dance, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that even in the darkest places, the universe is always watching, always waiting, always holding space for those who wander softly through the night. This has been Drowsy Discovery. Good night.